Okay, I think we can start the session. It's a great pleasure for me to introduce Terry Blevins, who is one of the most well-known world experts in process control. His CV is very, very long. I would like just to mention that he's a principal technologist of Emerson Process. He has 54 patents, and he has written many, many papers and books which are fundamental contribution in process control design and process control applications. He's also an ISA fellow, and he is a member of Control System Magazine Process Automation Hall of Fame. So please welcome Terry for this talk.
Yeah, thank you. Yeah, it's a real pleasure to be here and to talk to you today. Going back to about 2004, there was a very focused effort within the process industry by manufacturers to come up with a specification for wireless devices that all manufacturers could adhere to. That work was done jointly between major companies like ABB was part of it, Emerson, Siemens, a number of other companies that you're familiar with were part of that effort. That specification eventually then became the IEC standard for wireless HART. Now, in 2004, when this work was just starting, it got pulled into the meetings to look at how are we going to use this wireless transmitter out in the field in closed-loop control. And at first, in looking at that, it just looked like mission impossible to do that, because a number of things that we had always adhered to in the process industry in terms of sample rate, update rate, were being violated. But over the years, we found techniques then that allowed us now to work with these wireless devices in closed-loop control. So I'll be going through sort of this little history of how we got to where we are today in terms of that. And you can see then how we've applied it. One of the keys to that was to realize that we needed to go to event-driven type control. And so that's something that seemed to fit into the conference here. If you look at standards, usually they're a reflection of work that has already been done. That is, the ideas are proven out and that kind of thing. In terms of event control or event processing, there have been a lot of work within the process industry and within standards before this work in 2004, and I thought it might be appropriate just to touch on that very briefly to let you see some of these things that have been tried in the past in case you maybe aren't aware of some of this work. Then I'll be talking about the impact of wireless technology on how we do control and give you some examples of how that has been addressed. Looking at model predictive control, how to incorporate wireless measurements into that. And then looking at the future, which would be wireless throttling valves. So that's something that we're currently working on. So it's an evolving kind of thing, this whole world of wireless, and so I'll be touching on each of those things. If you look from a standard standpoint, one of the most important standards that was published within the last 20 years is the IEC 1131. Previous to that standard being published, there had been a lot of work in terms of graphical interfaces, in terms of function blocks back in the 80s. TouchSim was a commonly used tool. There were PLC manufacturers that have been doing ladder logic graphically and the equivalent of a sequential function chart. So there's a big, long history of how that would be done, and therefore the actual standard was just a reflection of that, a formalization of what was being done. In terms of looking at that, in 1131, it was very much backed by the PLC industry. Jim Christensen from Rockwell was the chairman of the working group that actually put together the 1131 standard. So the PLC environment very much picked up on this standard. And in terms of the use of that, they could use it the way they'd always done PLCs, a centralized type control, where things are structured, where you access I/O, you execute control, you then ship out the outputs, and then you repeat the whole cycle again. So in this way, you had periodic execution, and you had things being synchronized between I/O and control. So it fit in very well into that environment. Now, one of the things that was happening, though, when this standard got published, many manufacturers were looking at a more distributed environment. Fieldbus was really active. Profibus, Fieldbus Foundation, Ozzibus, DeviceNet, number of areas where we're looking at distributing I/O. And so the concept of having a centralized control and scanning just didn't fit in this distributed environment. So Jim Christensen, again, initiated work on a new standard to address this distributed environment. And that eventually became IEC 1499. That took about 12 years to actually develop. Now, unlike many standards, this one had very little background in terms of practical experience in industry. And that was one of the reasons it took 12 years to come up with it. The main difference between this and, say, 1131 is the top hat, which execution is triggered by event input. And resulting from execution, you could generate one or more event outputs. And the actual coordination of the events was done through something called an execution control chart. So this was conceptually something that could then be used to address a more distributed environment. And that was the hope. Now, when the standard was actually introduced, though, and people started to try to apply it, there were just a number of issues that came up. Concurrency, data consistency, some ambiguities that meant that you didn't get always the same type of results, even though you had sort of the same conditions. So this was an issue. So in 2012, there was a revision to try to address some of these areas. But in general, I think you could say that the standard itself has been interesting. It has had some impact on the industry, but I don't think it was as much of an impact as maybe Jim and some people that worked on the standard had hoped it would be. Just a lot of practical issues associated with this very generalized environment. Now, in some cases, that standard, though, was picked up. And in one case, it was in Fieldbus Foundation. If you actually look at the architectural document for Fieldbus Foundation, you find that this top hat is there. And there's further clarification of what goes on in terms of algorithmically what you're executing. But this is something that was picked up, but it was very limited in terms of the way it was actually applied. We had in Foundation Fieldbus the development of a schedule for execution of measurement and control. That schedule then was distributed down to the device level, and there was a distribution of time where all devices knew what time it was to a very precise value. And so each device, independent of everything else, could actually execute and be in total synchronization with everything else that fit the schedule here. So the event processing here was just really, I'm invoking you to maintain a schedule. And in many ways, you can look at this as we essentially duplicated what had been done in 1131 and PLCs. That is, you had synchronization of I/O and control and periodic execution. So the tools were used not to do something that was fundamentally different, but trying to do pretty much what had been done before. Now, in parallel to this 1499, there was this effort of 1804. And that was an effort to try to harmonize the different activities within the standards community. And so 1131 was definitely part of that. The 1499 was part of that. Some other activities were going on that impacted that. But this is the international standard for process industry function blocks, is the standard. Now, the standard has had an impact and is supported by most distributed control systems. But if you look at the way it has been implemented in a distributed environment, it wasn't really possible to synchronize I/O with the control. And so what you find is that in many implementations, the I/O is oversampled. That is, you're just constantly bringing that into your controller. And then when the controller executes control, there's very little delay between the I/O and it being used in control. So we've minimized any delay. So again, in this distributed environment, we're doing pretty much what we always did. That is, we had periodic sampling, we had periodic execution of our control. And so if you look at that 20-year time frame, manufacturers pretty well stuck to what they'd always known and done. But with the introduction of wireless devices, we really had to change. And so that's what I'll now be going into. So if you look at what's available today, most of your measurements that you would have in a wired environment are now available from multiple manufacturers that adhere to this wireless HART standard. So you have the basic kinds of measurements, pressure, temperature, flow, level, but you have other things like pH. So just about any kind of measurement that you can get with wired, you can now get with wireless. And you can get it from multiple manufacturers. The adoption of this technology has really been surprising. You know, if you said to me 10 years ago, how fast is this market going to grow? I never would have expected it to grow the way it has. But from 2009 to today, it's gone from about 0 to a $300 million market for these kinds of devices. So the adoption rate is really high. And the reason for that is that it solves many problems for customers where they need another measurement. They can't afford to run wiring all over their plant to get to it. Now they can do it wirelessly. So that's really driven it. And now the popularity of this wireless HART as the technology really goes back to the 80s when we had just analog or digital devices that were providing an analog output of 4 to 20 milliamp output. To calibrate the digital device, then there were communicator devices and control systems that could talk to the device over a superimposed signal that was then used by the device in terms of calibration. So we could talk digitally to the device even though it was working in the 4 to 20 milliamp arena. So this technology just really took off, and the wireless HART leverages off of that. It uses exactly the same protocol that was used way back here. So the 35 million devices that people know how to work with and do things, they can now apply that in the wireless world without having to learn new tools for calibration, setup, and that kind of thing. So that was an important thing. You know, from a protocol standpoint, there are a lot of ways you could do it better, but the overriding concern was bringing the customers along where they had huge investments in training and other things with the HART protocol. The installation of these devices, you can get fairly large distances between the devices and the access point, that is the connection to a gateway. You really don't have to have a line of sight. It's just amazing sometimes to see installations where they put in wireless. There's no clear line of sight at all. You know, there are distillation columns here and there. And, but the thing is by reflection, you can still achieve the signal and have connection. So it's pretty flexible from that standpoint. Now, when we talk about wireless communication, then we will start to get into something that's a little bit interesting here. With wireless communication, then wireless HART, there are two ways that are primarily meant for continuous control. One is something called just continuous, which means the device periodically wakes up. So you configure how often you want it to wake up. It senses the measurement and it then communicates that. The other approach is something called window communication, where the device wakes up periodically, just the way it did on continuous, but then it says, is my measurement, has it changed more than a certain threshold, a resolution or deadband? And if it hasn't, then goes back to sleep without communicating. Okay, so the end result of that is you now get aperiodic updates from these devices. So that can become a challenge because most of the control today based upon always having that measurement every time you execute control. This technology can be easily integrated into most control systems, so there are a variety of ways of integrating it, and so you can do that. And most manufacturers have done that. If you have a device that has power to it already, then you can access the information within that device by applying something called an adapter, so you can wirelessly communicate with the device. So you may have like a magnetic flow meter, which due to just the electronics and that are in that magnetic flow meter, you may have local power anyway. And so that power then can be used to power the adapter. So in cases where you have power locally in the device, then there's really little concern about how much power is used in communication. But in most cases, what you find in new installations or where they're putting in a new measurement, there is no power. And so then the device is powered by battery. So this leads us to another limitation or consideration, in that with a battery-powered device, most people you talk to in industry are saying, I'll only install this if I get a 5 to 7 year battery life. Now, to get a 5 to 7 year battery life, what you're really talking about is an 8-second periodic update for continuous, or if you're using window, waking up every 8 seconds, and maybe having a default of 32 or something. So much slower update than what we're used to. Now then, the rule of thumb has always been that you need to have a new measurement and to use that in control at least 4 times over your process response time, your time constant plus dead time if it's a self-regulating process. If you were to then use wireless, where you could actually update at least 4 times over the process response time, then you see you get fairly good control. That is, there's not a lot of difference between that and a wired installation. So that's what's shown here. But then if your update rate is 2 times slower than the process response time, then things don't go so well. Now, you could say, well, Terry, you know, I could just go in there and I could crank back on the reset. If it's aperiodic, though, how much do you crank back on the reset, right? So in general, you really can't resolve it that way. It's not a doable thing. So this is an issue. I guess I tell people up until wireless, the industry has very much just mimicked analog control. all the way going back to the 70s. And we've been very successful at that. That is high-speed update, high-speed execution of control. But now with this wireless world, you really have to take a different approach in terms of structuring the control. Now, one of the things you might think of is, well, why don't you put an observer on there? That is, why don't you just take the PID that I know and love today and just put an observer that's going to fill in for those times when I don't have a new measurement. And in actual life, you can do that. You know, you can take a simple single in, single output Kalman filter, and you can modify it where only if you get a new measurement do you update the residual that is actually then being used. And that works. And if you then look at the control is really quite good. But the problem and the issue for the process industry is throwing in an observer. You now then have to make the model match what's going on in the process and now explain to someone how do you tune the PID to work with the observer. And in general, that's a real barrier for the industry. We're very fortunate just to have people be able to tune a PID, let alone throw in more things that complicate it. So that approach, even though technically is very feasible, not very practical in terms of selling that idea within the industry. So that really forced us to start looking at how can we modify the PID to handle this aperiodic slow update. Now, to understand how we address that, it's interesting to look at how in industry the PID is actually structured. So if you go to the major DCS vendors today, they don't implement the integral action that way. The integral action is implemented using a positive feedback network, where that filter is just a first-order filter. The time constant is the integral time, and mathematically that is exactly equal to that, except where you hit limits. So you can do that little exercise and prove that to yourself. Mathematically, they're identical. Reason that manufacturers have gone to this approach and not that approach is, with that approach, you have to add in all sorts of ad hoc networks in there to avoid wind-up. With this technique, when you hit a limit here, your reset contribution is automatically limited. So it has real advantages in anti-reset wind-up, a very simple approach. But more importantly, we'll see later, there's a concept of something called external reset, where the input to our positive feedback network is coming from a downstream unit. So Shinsky at Foxborough has written a lot about the power of external reset. And in cascade control, override control, it's really fundamental to do the PID this way to be able to do good override and cascade control. So if you take this or that and you tune this for a lambda factor of 1, so your closed loop time constant is going to be equal to your open loop time constant. And your process, let's say, is just a pure lag process. Then if you change the set point, you see something that is quite interesting. The output only changes one time. Only one time for that set point change. Even though dynamically the process is changing all during that time frame. Now you look at that and you say, well, Terry, that's just zero pole cancellation. It is, but if you look at it in terms of this implementation of the reset, what you see and what the true meaning of zero pole cancellation means is that dynamically this is exactly matching that process, if that was a pure light process. Okay, so if you get that understanding that this is actually representing the process dynamics there, the response, then you say, what do I do when I don't have a new measurement coming in? Well, if this filter is representing my process dynamics, I could be changing set point even though I don't have a new measurement. And my output could be changing in response to that. And for sure, my process is going to respond to that. And therefore, really, that filter should also be responding to that. The problem is you don't have a new measurement update coming in through here. And therefore, what PIDPlus does is it holds the last filtered value when you had a new communication. So whatever the value was at that point, it sort of clamps it at that value when you have a new measurement. And so the filter continues all the time, and its output then gets used only when you get a new measurement here. So that's what we call PIDPlus. Now, for derivative, if you have derivative, then you really need to restructure derivative too, because normally the derivative is based upon the time between executions of control. So it's the delta t divided by the delta change in era. Since we're not getting a new measurement, except very slowly getting new measurements, it would look to the derivative as though you're getting steps and change. And you take a derivative of that and you get a large spike, don't you? So we then take the derivative over where the delta t is the time between new measurement values. And so that was a change there. Now for all of this to work, this PID then is executed much, much faster than the update here. So you may, say, have a measurement update of 8 seconds periodic. You then would probably be running this maybe at every 200 milliseconds. So if you think about the previous implementations where the I/O was oversampled so that the control, when it executed, had a new value that was fresh. Here, we've just flipped it 180 degrees. The actual control is executed very fast so that when we get a new measurement coming in, we take action upon that immediately. There's no delay. And that means we then minimize any delay introduced into the control. Okay, so those are the concepts of PIDPlus. Now, if you then take an example where we've tuned with a lambda factor of 1, we had a resolution of 1%. So it's non-periodic update. Then on a set point change, we're comparing a wired transmitter with PID to PIDPlus with a wireless transmitter. And you notice, at least for a set point change, very little difference. For an unmeasured disturbance, you notice you don't do quite as well with the PIDPlus. And you wouldn't really expect to, because you're only getting an update every 8 seconds. The disturbance could occur anytime during that 8 seconds, right? So you wouldn't expect it to be equivalent, but you notice that every time you get a new measurement update, the valve is at where it would have been if you had been with a wired transmitter. Really interesting behavior. If you put this together and sort of look at it and watch it do its work, it's sort of fun to see that happen. Now, you notice the integral of absolute error for the wired versus wireless isn't that much different. But the number of communications for the wired, we had 692 new measurements. For wireless, we only had 25. So reduction by about a factor of 30 in terms of updates. And what that really translates to is battery life, right? You don't have to be updating every second. Yeah, there's some things that are being published out there that say have to update every second. Well, your battery is going to last about 3 months at a 1-second update. Now then, in terms of looking at what happens on loss of the wireless measurement, a lot of people have installed these devices and found they're extremely reliable. But there's always the question of, well, what happens if I'm using a closed loop control and I lose communication? Well, if you're using PIDPlus, the behavior is really quite nice. If you're using PID and the same thing happens, not so nice, right? And this is the equivalent thing where we lose communication in the midst of a disturbance going on. And again, you see the behavior of PIDPlus is much better than PID. So we tell people that if you're going to use PID, because maybe you have a slow process, you can get a measurement update at least 4 times over your process response time, then it's critical that you put in logic to shift that control to manual if you lose communications. If you don't, you get that kind of thing. But with PIDPlus, it just automatically handles it the way it's structured there. So in some cases, this PIDPlus is just a standard feature of the control system. To actually get it, you just click and you've got that capability. If you have a wired transmitter and you by mistake click that, it's no problem, because it then would behave exactly the way the regular PID would behave. Right? Now, when we were initially trying this out, we wanted some field experience with this wireless technology. So in 2009 timeframe, we were working with Broadley James. They're a manufacturer of equipment that is used by the pharmaceutical companies to develop their different products that they're making. So the biological ones would be done in this disposable bioreactor. That's one of the ways you can do it. So we're working with them on something else, but Scott Broadley, the owner of the place, was interested in wireless, and so we instrumented their bioreactor with a few wireless measurements. And in some respects, it actually makes sense, because these disposable bioreactors are actually on wheels. They cart them around between different locations. Okay. So in that case, then we picked pH and we picked temperature. And we had it set up where we could sort of shift between wired or wireless for the control and PID or PIDPlus. Here we're then looking at the temperature control. In this case, it's just wireless. And if you were to compare it to the wired response, there's really zero difference between the two. For pH, for extremely small changes here, the response was really the same as if you'd had a wired transmitter. Now then, in a way, it wasn't a very good field trial because the process was so slow. You look at the time units down here, and you could have used PID with this wireless measurement. Wouldn't have required PIDPlus. Okay, so we wanted to try something faster. So we're fortunate in that we're located in Austin, Texas. And University of Texas is located in Austin. And they have this J.J. Pickle Research Campus. So if you're ever in Austin, would encourage you to go out there and see this. It's really quite a nice complex. But they do all sorts of things there. But in one small corner of it, they have their separations unit, where they have 2 fairly large distillation columns. And so they use those in a variety of different ways. So we took one of those and we made their steam flow to the reboiler wireless, a wireless transmitter. And the same thing on the actual pressure of the column. Both extremely critical measurements. And this is showing, I think, the pressure control, where we were doing wired versus wireless. So we did 2 campaigns, one with wired, one with wireless. In this particular case, there was 0 change in tuning. We wanted to demonstrate that you tune the controller just the way you always tune it. You don't have to worry about how often the measurement's being updated. And so in this particular case, we used exactly their tuning. And if you look at the integral of absolute error, there's not a lot of difference, but the number of communications is just radically different between the two. So again, with wireless, executing much slower, you can achieve pretty much the same response. So we're working in other areas today, and on just plain PIDPlus, we're doing some work with a major oil company right now looking at that. Anyway, for use in upstream process, oil and gas. And so a number of other things going on that I didn't have room in here to show, but one of the newer things that we're doing is at this J.J. Pickle site, they have installed a divided wall column. So they designed it themselves. They had a number of major backers like Eastman Chemical that put this in. And so this divided wall column is a fairly new technology, at least to the U.S. Europe is ahead of us in that respect. But it allows you, by putting a wall down the middle of the column, to do ternary separation. That is, separate three components using just one column. Normally it would take two columns to do that. In terms of that, we're working with them on the control, the design of the control for the column. On the composition control on this, we're using temperature as an indication of composition. It's extremely interactive. There are papers that people have written just on how to tune the temperature control to avoid interaction. So it's a highly interactive process. That's one of the disadvantages of the technology. So what we have done is use model predictive on this temperature control to decouple this interaction. And in this particular case, all the temperature measurements on the entire column are wireless. They don't have wired temperature measurements. And so we then were forced to start looking at, well, how do we do model predictive control using a wireless measurement? Willie Voisinitz did a paper on this yesterday. So if you want to know more about this, he goes into it in much more detail. But just to give you a highlight of that, with model predictive control, you basically are comparing the value you are sensing out here to what has been predicted from your model. So you're actually, in this case, you do have a model. You have to have a model, so it's no extra burden. But it depends upon that new measurement being their ever execution. So with wireless, you won't be able to do that. So basically, this model update with wireless measurement is maintained at the last bias that was used, and only update that value when you get a new measurement coming in. So that was the minor change that was made to this. We flagged to model predictive control the fact that you have a new measurement or don't have a new measurement using something called status. The status accompanies each input and each output. So outputs and inputs have both a value and a status in this 1499 world. And so we have then where it's going to 0 there, it's indicating a new measurement. So if you notice here, then the measurement is being stepped because you're only updating I think in this case, every 16 seconds. So it wasn't updating that often. But the actual control looks very much like you're using a wired measurement, because in between updates here, you're actually using the model value, and the model continues going. And so you can fill in between samples using that technique. And many model predictive products, they're designed to automatically invoke simulation, that is, to use the model when a measurement fails. And in our particular product, we also do that if you have a lab sample where you don't have an update very frequently. then you can then invoke maintaining the last bias until you get a new measurement. So we were able to very easily adapt that to do model predictive control. And we actually commissioned the model predictive control here last month. That was sort of gratifying, because we've been planning on this for about 2 or 3 years. I commissioned it. Again, everything was wireless in terms of the measurements of temperature. And we were able to achieve much better control than you could get with just plain PID because of the interactive nature of the process. And that has a direct impact on composition. So that's with PID control, that's with model predictive on the side draw. So new things we're working on. One of them is wireless throttling valve. I gave a presentation yesterday in terms of wireless throttling valve and go into it in much more detail than here. But today you can buy on-off valves that are wireless and implement discrete control, that is, regulate turning on and off the flow. And there are a number of installations where people have done that on tank level control, tank temperature control. So today the technology is already there, where you can get a 5-year battery life, you can have on-off valves, you can be sensing level or temperature, and that's a reality today. But in so many cases you need a throttling valve there, and so that's the work that's going on today, is how do you do that? Now conceptually, all you would need to do is say bring back maybe the position of the actuator. And this would be where you'd be using what's called external resets. So rather than using the output in your positive feedback network, you're using the actual position going through there. Now, if this actuator was very fast, there wouldn't be any difference between that and that, would there? But if this is a motorized actuator, it'd be very much a difference. And automatically, that's accounted for if you're using the actual position in here. So that's one of the advantages of this external reset capability. So conceptually, you would just do this kind of thing. But the thing is that there are a number of technical issues that we face. And one of those is that most of your power that you're going to be using here is changing the position of the actuator. So you're going to have to be activating something that's going to be changing the position, and that requires power. So you'd like to minimize that power. And oftentimes if you go into the process industry and you look at a valve, it's just almost constantly hunting and changing positions, right? So again, you could very well burn out a battery by those frequent changes. So that's one issue. The other issue is it could take a long time for this output to go down to the actual valve itself. And that's because in wireless HART, all the measurements are scheduled. So that's scheduled communication. You don't ever have to worry about this measurement colliding with another measurement in terms of reporting, because automatically your gateway establishes schedule, and automatically then things are communicated at a very precise time. But on the going downstream today, the gateways don't allow you to schedule that activity. And so you sort of have to find an open window in the schedule to actually be able to communicate, and that can take a number of seconds in some cases. So that's another important issue. Similarly, if you're getting a sensing of the position due to maybe the response to your writing to this, it can also take quite a bit of time coming back. So how did we address that? Well, one of the things that we've done is put in an event-triggered output. So on your measurement side, we said, well, if you execute periodically, that is, you wake up and do something, then if the value is changed by more than the dead band or resolution, then it will report. Otherwise, it doesn't report. And only if time has passed for the default time and you have not sent an output, it's going to send one anyway. So that's the default. So we sort of applied the same thing on the output side, where the PID is calculating an output, but it doesn't necessarily get sent to the actuator unless these criteria are met. Okay, now you say, well, isn't that going to cause all sorts of hunting and oscillation and other things? Turns out not so if you're actually implementing it this way. So what is done here is that to account for the delay going down, we have worked with the Heart Foundation trying to come up with a new heart command. So when you are asking for a change in valve position, you say, I'd like the valve to change to this position, and please do this X seconds from now. So that's the time to apply. So it may take 3 seconds to get down this time, may take 5 seconds to get down next time. But if you say the time to apply is 6 seconds, you know always when you ask for a change, 6 seconds later that valve is going to change. Okay, so even though we can't measure the valve changing, we know it's changing. So that response then, we then can calculate and compensate when we do a change in output, compensate for the time to apply in this feedback to our positive feedback network. Okay, so with time to apply then, you may have varying amounts of time to get down to the valve, but always the valve is going to change in the time to apply time, so that we then can compensate for that. So in a simulation mode, this is what this looks like. In the first case, I think we had 3 seconds going down, 3 seconds coming back in terms of the signal. And you notice no hunting, no oscillation, very, very well behaved. The only thing you have, though, is there is a delay, the time to apply between you making a change and that actually then going and being acted on. In the second set here, I changed it to be 6 seconds down and 6 seconds back. Now the important thing here is that the tuning of the PID here was based on a wired valve and that process. When we went to wireless, we didn't touch the tuning. And we didn't touch the tuning going from here to here. Okay, so this technique then allows you just to worry about what's my process gain and what's my process dynamics, setting your tuning on that, and the fact that you have delays going down, delays coming back, or you're not updating your measurement that often is really not a concern. So here we've combined wireless valve with wireless transmitter, and the two very much work together. So again, if you look at that, no hunting, no instability, and yet we were using 3% reporting deadband on the measurement. Now you can do a lot of things in simulation, and then you get into real life and you find out I didn't account for something, right? So one of the things that we do is go to the field, like the customer site, and try out this new technology. But also in the particular case of this throttling valve, we're really fortunate in that one of the divisions of Emerson is Fisher Controls. So they have one of the world's largest flow labs in Iowa, going up to something like 36-inch line size. So they can test any valve that is manufactured there. And so they gave us a small corner of their lab here where we were then working with valves that were of commercial size and at flows that were commercial kinds of things you see in an operating plant. So in this particular case, we had a valve downstream of this prototype wireless throttling valve. By having this valve downstream, we could introduce disturbances into our process. Okay, so we could test both set point change and disturbances, unmeasured disturbances, by changing that valve. The actual prototype doesn't show up here real well. It's over in that area there. Okay, so if you look at that particular process and you're using a wired transmitter, wired valve, then this is the response that you get. And you notice it isn't a perfect smooth curve here. There's some real interesting dynamics going on between these tanks and that flow loop. Okay, but it's what it is. And so that's what it was with the wired transmitter. In this particular case, we used tuning established by Ostrom-Hagelin's relay oscillation. That's sort of the thing that we have in our control system. So we wanted to prove that you don't have to be an expert on tuning. You don't have to futz with tuning. You could just use what comes out of your normal tools. And so that was what we did here. The actual process response time on this was about 3 seconds. Now, all the testing with wireless was pretty much done with an 8-second update. So we're doing control with fairly fast process and a slow update. This was where we were introducing in that downstream valve changes in that introduced a restriction, a variable restriction downstream. And so our control loop then had to compensate for that. And you notice it had to do quite a bit of work over in here to get us back to set point. So it's for a wired installation. Now then, where we had a wireless valve, and we had an 8-second time to apply. This is what happens. So again, no hunting, no oscillation, no problem with this. You do notice, though, the time to apply, that is that delay in actually taking action on what's going on. Where we then look at unmeasured disturbances using the wireless valve. Again, the response is really not too shoddy compared to the wired. Very much good control, stable control, bringing us back to target. This shows us then the wireless transmitter and wireless valve working on that flow loop in the lab there. And so in this particular case, we had 8-second update on the measurement, 8-second time to apply going down to our throttling valve. And you notice on set point changes, it's not as responsive as you might want to go there. But once it gets to target, absolutely stable, no oscillation, no hunting. Similarly on our valve, you notice that behaves well. Here's where we're doing unmeasured disturbances to a wireless transmitter, wireless valve. And again, you notice very good control is very much achievable with this liquid flow at about a 3-second process response time using 8-second updates. Right? So we tell people that wireless control is not just for your slow processes. It's for your liquid flows, it's for your gas flows, things that have 2 or 3 second response time. And you can address those with 8-second updates as long as you don't have to compensate for an unmeasured disturbance faster than your measurement update, the wireless update. And honestly, if you go out and look in industry, there are just a whole variety of loops where that response to an unmeasured disturbance isn't that critical to get back to there within 8 seconds. So I think the techniques here very much open up the world of control, not to just the slow stuff, but to address these faster processes. Okay, so in summary then, we've done quite a bit of work with this. The PIDPlus has been applied in a variety of applications very successfully in this. With model predictive control, in most cases, it's really not much of an effort to be able to accommodate those wireless measurements. If your process is fairly slow, you probably don't have to modify the model predictive at all. But on some of these newer MPCs, like in this particular case, it executes as fast as once a second. In those cases where you're controlling maybe a fast process, then it would be necessary to make those changes in model predictive that I talked about. And in the future, then these wireless throttling valves are coming. And in terms of applying those, we don't really anticipate any problem in doing that. There's a lot of research and work going on to reduce this time to get down to the valve. So there's something called downstream publishing, which is in the wireless HART standard, but most of the gateways today don't support that. So once we do that, then this time to apply can be greatly reduced and take out some of that delay in response where you're using a wireless valve. Last year, Willie and I and a couple of other people put together this book. It sort of summarizes what we've done over the last 10 years in wireless control. Now, I'm not mentioning that to get royalties, because all the royalties for this are given to the University of Connecticut. So we just give all the money to them. But just mentioned it in case you're working with wireless control, then this is something that could be maybe helpful to you. There's a website there that goes with the book. Anyone can access that. And for each chapter, there's a workshop. And you can then go to that website and see the solution to the workshop as a YouTube video. So there are 10-minute YouTube videos for each chapter. So, if you're looking at this wireless control, wanting to show it to someone, well, this is there. There's a 10-minute YouTube video on each of the chapters. So you can sort of demonstrate commissioning of a device, demonstrate control with a wireless valve, wireless transmitter, and that kind of thing. So hopefully you'll find that of help if you're involved in wireless control. So I guess at that point, I'll be glad to entertain questions.
I think we can take a couple of questions.
Hi, thank you for a very enlightening talk in respect to where event-based control may come. I have a following question. In your industry, you don't see much of collaborative controllers, do you? Since if we work with autonomous vehicles or robot humans, then we want to do a task, we have to collaborate. It has to be described in some logical way. Then the timing issues and the changes are becoming problematic as far as information, what do I do, and so on and so forth. I don't know if I'm correct, but you don't see a lot of that in the industry you work with.
It just depends upon, I guess what area you're looking at. With Foundation Fieldbus, each device is sort of autonomous, but they're actually tied together through the schedule that gets distributed to, and so they're working together to achieve some goal, and those could be like 4 or 5 devices that are all working together in that environment. So that's the best example maybe of
So the question then is when you have more of this collaboration, communication, and information exchange, and so on and so forth, what's your prediction, since you know this field so well, with respect to the applicability of wireless?
With wireless, there's discussion of can we actually move things down to the devices in terms of control and that. And actually, I've sort of lobbied against that personally, because one of the things that we did in Foundation Fieldbus was we moved control down to the field device. So it had PID and other things. And if we could rewind the clock on that, we probably wouldn't do that because of the added complexity for the end user. And that's been a big barrier in terms of Foundation Fieldbus. So I think a lot of this has to be over time. Maybe with time, maybe things will be better in terms of that. But we always have to take into account, can it be maintained? Can it be easily installed? If it shuts down at midnight, who's going to fix it? That kind of thing.
Thank you very much.
Sure.
Any other question?
Good morning, everyone. Thank you very much for this nice presentation, even with
wireless control. It's really interesting. Just a small question. In your controllers, what distance you are working on means wireless communication? Is it within a fixed zone or long distance?
Yeah, the access to the wireless is through something called a gateway. The gateway can then be connected into Ethernet, and so you may have in a large plant you may have 4 or 5 gateways. Each gateway is sort of responsible for maybe a process area in your plant. Gateway can have up to 100 devices associated with it, 100 wireless devices. And there's something called an access point. That means the antenna that really is used doesn't have to be at the gateway. It can be remoted away from the gateway. So you can locate it maybe on the top of a tower, or you can put it in different places. So there's a lot of flexibility in laying it out and that kind of thing. But most companies right now today are laying out wireless where it covers the entire plant. So if they want to install something, they don't have to go back and change gateways. They just have access to it that way.
And another thing, you work on PIDPlus wireless. Is there a PIDPlus wired version as well? Means the idea is to reduce the measurements and then translate via the wires. Does it exist as well? Or because you present PIDPlus with wireless, so do we have a wired version of PIDPlus as well?
Yeah, actually, it's a little bit deceptive here. You know, I presented it in terms of the context of wireless, but PIDPlus can be used with any analytical measurement, like a gas chromatograph. Just anything that's not updating, you only are getting aperiodic updates. And so there are a lot of spectral analyzers, gas chromatographs that you just don't get a continuous indication of what you're interested in. But PIDPlus is really a nice way to handle that. And you know, before that, what happened was people took the PID and did a bunch of ad hoc stuff to it, right? Turn on the reset for 10 seconds, turn it back off when you get a new measurement or something. And it was all because you didn't have a good way to handle the reset. Well, with PIDPlus, you can use it for that.
Thank you.
But I mean, I guess, Terry, the straight answer is that if it's periodic, you can use PIDPlus and do a good job there.
Oh yeah, you can. It's really nice in that it's like this continuum all the way from regular wired all the way up. And only once you get past about 30 seconds do you get into this thing of, well, you really don't need to be using PIDPlus. You know, you could use regular PID, but that window of 0 to 30 seconds is really where it has its major benefit. Yeah.
I worked a little bit in this area with the National Institute of Standard Technology and people of Europe. And the question is, and what I ran into is that there's not a lot of consideration regarding security in this workers. Do you have any comments on that? Is your industry or your company trying to address this?
Yeah.
Because very easily, if you go to a factory, because of the distances you mentioned, they're not small. Facing security, if people don't worry about cryptography, this is pretty well handled. But what we face is people that they're actually attacking the algorithms. The algorithms that we as control people use for sensing and control. Any of that has come to your part of industry as a concern?
Well, when the specification was being written back, 2004 time frame, Tom Finney from Honeywell at that time was involved, really an expert in security. So all messages are encrypted. The encryption key is put into the device using a handheld, not communicated. And there are two keys. There's a network ID, and then there's something called a join key. So you actually physically attach to the device, add it in at that point, and those are then used in the encryption algorithm. So in terms of someone being able to get at the information that's being communicated, little chance they'll ever be able to do that. There's hardware encryption that's going on, so it's really fairly lengthy encryption technique. But there is this thing of if someone wants to do damage and goes outside the plant and they want to disrupt things, then that's more of an issue. And I don't know if there's really a good answer. I mean, it's sort of like, well, if someone wanted to, they could come in and tear out the wires that are on your plant too. You know, it's just a thing of security of the plant, I think.
I think we can.
Yes.
Again.
Okay, sure.